Hello, this is the lab 3 for Ian Mcfarlin.
And Inirio.
So this is the code for our lab. This first file is the file that basically holds it all together. It takes the inputs, the outputs, and sends it out through the VGA, the ALU from the previous lab, the keyboard, and the RAM. Here we have the pre-existing code for the ALU from lab 2. It hooks into the ALU from lab 1. Here we have the pre-existing code from lab 2 of our ALU. It hooks into the ALU itself, the hex display, and the decoder. And here we have the basically control file for the VGA, which is hooking together the inputs from the main file and using them to communicate with some of the smaller modules to make the VGA work. For our display, we have bouncing squares that signify the output. So to do that, we needed to have each square have coordinates, each square have its own module, and we also needed multiple if statements to allow for squares to appear when the value on the output of the device was greater than the necessary number to have that square appear. Here we have the file for that helps to allow the display to display. It goes through from one end of the screen, one side of the screen to the other, resetting down a row of pixels and going again. And that's basically what this is essentially doing. Next we have the file that actually allows the squares to appear. It specifies a default size, starting position, the X and Y, and a starting direction in the X and Y, with the 1 being to the right or up, and a 0 being to the left or down. And basically calculates the current dimensions of the square along with any changes so that it can be animated as it moves.
Since we have a USB host pre-installed into the FPGA board, all we have to do is gather the keyboard inputs from the USB. This is initialized as a USB-D variable and its clock. Since the keyboard codes break with the hexadecimal value of F0, we make a couple of constants for special cases like this. These cases are break to initialize that the key input has ended, left and right shift, noting that the shift keys are held down, and caps to signal if caps lock is on or not. Then we have a PS2 filter to filter the raw USB data into a more readable signal, since USB and PS2 connections both carry a lot of noise, especially from a keyboard input. This would help us initialize what the keyboard is actually typing out to and what the value should be. I used a state manager to check if the keyboard is still receiving input or if the keyboard is done inputting. The way I've done this is by having the state key be resetted every 10 8-bits input. This also includes the break variable F0. After filtering out the raw data for the keyboard, I was able to give some conditional statements that would differentiate between different combinations. For example, if I were to hit caps lock and type a letter, then the uppercase letters would be chosen instead. This is represented by the lowercase variable. Moving on to memory, we decided to create a 256-byte random allocated memory register for our FPGA board. The way this works is by having an 8-bit input data be allocated and pushed into our memory register during the process. Ideally, this memory would also be popped out of memory after the process has ended. Since our memory is a multidimensional array where each slot is 8 bits and there are 256 rows of them, this memory can also be described as a stack. Ideally, I was trying to create a pointer to the stack to show that the memory is working completely, but deemed it too difficult given our time frame. So a data written into memory is good enough to show how random allocated memory would work.
Here we have the Ascii Key Library, which allows for the scan code from the keyboard to come in and be interpreted into an ASCII code, which can then be later interpreted into something that's displayable and usable as an input for we have the uppercase ASCII codes here, along with symbols for the numbers, and here are the numbers and lowercase letters, which are decided based on an input that tells what the case of the letter is. Here is our FPGA. It still has all the same functionality as the previous lab. You put all of them up, you can see that they go to show the opcode or the instruction and the input values. If you turn on the display, we have for 000 we have negate A. For 0100 we have A plus B. With an overflow and see out. My board's also kind of finicky sometimes, so B value sometimes stays. We also have at 1010 A and B. Which only goes on when they're both the same. And those are just some example ones to show it still works. We also have a Vga display that when the output changes, bouncing squares come to signify the output. This works through all the modes. And yeah. We also have a switch for adding the current A and B values to memory, which is right here. It does add them to memory, and yeah, it adds them on when it turns on, and then it moves to the next address. We had wanted to have the keyboard work for the input, but whether it's because of it being Bluetooth or maybe because this is both a keyboard and a mouse USB, it just wouldn't work. And there were no other USB keyboards available to me at the time to test, and it just would refuse to take the input from the keyboard. The code seemed like it should work. And yeah. The VGA, for the most part, was a success. It does work and allows the squares to bounce around, and it shows the correct number of squares that correspond to the output. However, we had also wanted to show actual text, but that seemed to be a bit of a more difficult challenge than we would be able to accomplish, so we had to settle for just showing the output in a different way on the VGA.
Going off from what Ian said, I do believe that our VGA display and memory allocation was a success. However, our keyboard input was not, in terms of displaying actual ASCII characters and numbers on a screen. But I do also believe that we could have improved in both the keyboard and the memory allocation. Like I stated before, the memory allocation could have had a pointer and stack system rather than just allocating memory